Today, Java CP, Lesson 6. We're going to be learning about the range sum query, which is going to be very helpful. So, to start the lesson, we have a bowling problem. So let's say I have a bowling ball that can hit a certain number of adjacent bowling pins. Each pin then has a certain score. So corresponding to the pin, if you knock this one down, you'll get 2. If you knock this one down, you'll get 5. And each of the pins have an index. So tell me what score I can get if I knock out all the pins from a left index to a right index. So the problem here is basically to just get the score from the pins 2 to 6. Saying that I knock down the pins 2 to 6, then you need to get the score, which is 2. I can't speak. At index 2, you'll have knocking down the pin at index 2, you'll get 3 score. Knocking down the pin at index 3, you'll get 2 score. 4, 1 score. 5, 4 score, and 6, 3 score. Right? So normally you would probably put this into an array of some sorts and just from index 1 calculate to index 6, right? And in other examples, from index 1 to index 2, which is a total of 8 score, index 3 to index 5, a total of 7 score, and index 0 to index 3, which is a total of 10 score. So here is one solution, right? Here, the question we're the set of pins we knock down is 2 and 6. And so the score for 2 is 3. So we add 3 to our sum, right? And so within this loop, j is equal to 3. Wait, no, I did that wrong. My bad. In this loop, j is equal to 2. So at index 2, you'll have 3 score. And so the sum, you'll add it to the sum. And so that's 3 score in total. Now you go to j equals to 3 because j++, the next loop, you'll have at index 3, 2 score, right? And you'll add 2 onto the sum, which gives you 5. And now you have a sum of 5, and j is now equal to 4, right? Because we're not yet at 6, so you just keep on looping. At index 4, you have 1 score, you add 1 score, you'll get 6. And you just continue on. Index 5, you have a score of 4. You add that to your sum, and you'll get 10. And since it's inclusive, you go 1 more. J is equal to 6, you loop again, and then you add 3 score, equaling a total of 13 score, right? Khan Academy or other online tutorials. I'll take that as a compliment. Now, so this is the basis of nested for loops, right? And so now let's try a problem. DMOPC 14, deforestation. So the problem statement, there is a row of n trees. Each and every tree has a mass. How much wood will he get by chopping down all trees between indexes L and R? So this is very similar to the situation I just explained. It's just the bowling pins are really replaced by trees, and the masses are variable. Can you solve it? Submit your solution onto Dmodge. Thank you, Ryan. And let us know how you did. And yeah, we'll just wait for someone to finish. If you need help with the problem, you can let me know.
Yeah, this problem isn't anything complicated so far. Just try the strategy that Jake was talking about earlier, about doing the nested for loops.
Yep, there is a... If you want another peek at it, you can look here, but try not to copy code word for word and try writing it on your own. That's good advice I could give you.
It'll also help you practice your demosh skills a little bit more about submitting to problems. Xiao said, I will
line.
line by line instead of word by word.
Yikes.
Smart. This is the kind of big brain attitude that we need to do competitive programming.
Thinking outside the box.
Yeah. Okay, who's going to be the first one to solve it? Let's see.
Gotta get that competition, competitive attitude.
Yeah. If you have any questions, just like put them in the chat.
Create objects.
You don't need to create objects for this question. It's basically the code that is shown, like is almost already your solution.
Yeah.
Yeah, objects not necessary for this problem. If you want to remember how to create objects, you can look back at our previous lesson when we were talking about sorting. We talked a little bit about classes and objects there. But no, objects won't be necessary because you can just hold the mass in an array, right? So if you submitted and you got a score, you can put that in the chat or like some observations that you made. Don't get overwhelmed by all of those different kinds of variables that are in the problem. It can be very easy to get overwhelmed by that, but you don't have to pay too much attention because we already explained that problem and what it was. And it's very similar to the bowling pins problem. Do you guys need some hints or are you guys still working on it?
Has anyone tried submitting yet?
The good thing is if you submit it and then we can go take a look because we're also on the website as well. Oh, okay. Let me see what's triggering the no such element exception. Okay. Oh, okay. So remember, it's not exactly what we coded out, because that one is just for the bowling pins. You have to look at the input specification. So it says first line is n, so you want to read n. And then lines 2 to n plus 1, which basically means the following lines, is the mass. So you want to read that the mass after you read n. So you read n first, and then you read the mass of every tree, right? And we know that there's n trees. And then after that, we would read the integer q, right, which is the number of queries. And then the next q lines will contain the integers a and b. So you want to read n, all the masses of the trees, read q, and then all of the queries. So yeah, that might help, I think. Was the n number inclusive? Yes, it's inclusive.
Yep.
Because if you see the output specification, it says for each query, print the total mass of the trees at position I, such that I is less than or is greater or equal to A and less than or equal to B. So it's inclusive. Also, if you're getting error messages in Java 15, you can try Java, I think it was Java 8. Okay, let's see. How's it going? Hey, okay. Looks like Andrew's got it. Oh, okay. So okay, that's great. Okay. Andrew got 4 test cases out of 6. Yeah, okay. So that's our first correct submission. So I'm just gonna move on. You guys can work on this afterwards, but.
Here, I'll stop sharing.
Oh, okay. I'll start screen sharing.
Yep.
Okay, good job, Andrew. So.
Congrats on being the first.
Yep. Okay, so you actually got the best score with all the knowledge that we've told you so far, right? So, but like a 7-pointer is never going to be that easy. And here's why. You might get TLE. So you might be wondering, why are you exceeding the time limit? Is my solution too slow, right? So let's take a look at why your nested loop solution might be too slow. So let's analyze the time complexity of a code like the one that you see on the right. So think about how much times does sum plus equals, or basically just increment sum by pins at j. How many times would this piece of code run in the worst case? Think about what happens in the worst case scenario. How many times would sum plus equals pin at j? How many times would that run in the worst case? So I want you to think in terms of the number of queries and also the number of pins. So what's the worst case scenario that can happen? How many times would sum plus equals pins at j run? Okay, so we got a couple of guesses. So a couple thousand times, got 1,000,000. All right. I want you to think in terms of numbers of queries and the number of trees, right? So how would you express that as a mathematical expression? So I guess you guys were very close. Yes, so Timothy got the right answer. It's trees times queries. So if every single query, I'm asking you to sum up the masses from the beginning to the end, then what's going to happen? Then every single query, you're going to have to go check every single tree, right? And add it to the sum. So if every single query, you're checking every single tree, then the number of times that code is going to run is going to be trees times queries. So yeah, so Andrew got that right as well. It's 1,000,000 squared. And that's a really big number that even your computer, which is super fast, would not be able to calculate in the time limit that DMOJ has set for your problem. So if you consider L is equals to 0, R equals number of pins minus 1, which is basically the entire thing, then it's number of queries times the number of pins. And that's 1,000,000 times 1,000,000, which is 10 to the 12 operations. And that's a lot of operations, right? So Java can usually handle around 10 million to 100 million operations a second, right? Depends on your computer, but usually it's around that. So your code is definitely going to be too slow, like 10,000 times too slow. So this solution can only get you partial points. When you're doing a contest, it's perfectly fine to write this kind of solution if you don't know the fastest solution, because you're going to get partial points, just like what Andrew did with his code. You're going to get some of the points, not all of them, but better than nothing, right? So there's always this very trivial solution that you can write up. But if you want to get the full points, you have to use some math tricks. So what are these math tricks? Then we're going to explore that. So what kind of crazy math tricks can we use to make this code faster? How can we use the knowledge that we have that all of the pins that we're going to calculate are right next to each other, that they're adjacent? So let's take a look. And also, this is not the proper way to analyze the time complexity. If you want to know how to do that formally with complicated mathematics, you can click on that link. So the mathematical trick that we're going to employ here is called prefix sum arrays. So what is a prefix sum array? Well, it looks like an array like this. So every single element of that array would hold its value and the sum of everything that comes before it. So you see that 0 holds 0, right? We're assuming that there's nothing at 0. 1 holds the element at 1. 2 holds the sum of 1 and 2. 3 holds the sum of array elements 1, 2, and 3. And 4 holds the sum of array elements 1, 2, and 3, and 4. So every single array element holds the sum of itself plus everything that comes before it, which is basically what I just said. And the sum of elements between L and R is equal to PSA at R minus PSA at L minus 1. PSA is just short form for prefix sum array. That's how I name my array. So that's just, you can replace it with your own array name. But it's the right index minus the left index minus 1. So let's see something cool here. Like, why is this true, right? Well, okay, let's think about it. So you want to find the sum from indexes L equals 2 to R equals 4 in list A inclusive. So A is the name of the array. So what would we do? Well, we would follow this formula, right? We would do PSA at R, so PSA at 4 minus PSA at L minus 1. L minus 1, 2 minus 1 is equal to 1. So what I am claiming is that PSA at 4 minus PSA at 1 is equal to the sum of all the elements between 2 and 4 inclusive. So let's see the magic here. So let's write out what is PSA at 4. Well, let's look here. PSA at 4 is equal to A at 1 plus A at 2 plus A at 3 plus A at 4. And then what's PSA at 1? PSA at 1 is just A at 1, right? So A at 1 here cancels out with negative A at 1 here. And what do you have? You have A at 2 plus A at 3 plus A at 4, which is your answer, right? It's just the sum of all of the elements between 2 and 4. So this is kind of like a mathematical proof here. You can just visualize it as like this in variable format. And it shows why this formula holds. If you want to find the sum of elements between L and R, you do PSA at R minus PSA at L minus 1. And then it will tell you all of the sum between L and R. So this might take some time to internalize because it's a lot. But let's see how it can be done. Well, this is the code for the prefix sum array. So first of all, we're going to create a scanner, and then we're going to read the number of trees, and then we can create our prefix sum array. And I do num trees plus 1 because I don't want anything to be at the 0th index. That's because if I want to find, for example, all of the trees masses from 0 to something, well, L minus 1 would be -1, and -1 is not a valid array index. So I want to shift everything over, right? So what do? Well, I start from I equals 1. I go to PSA.length, which is num trees plus 1. So basically, I'm shifting the array 1 index to the right, just out of convenience, because you might end up with like a negative index if I equals 0, right? And what you do is just very simple line of code. PSA at I equals PSA at I minus 1 plus in.nextInt. So why does this statement hold? It's because PSA at I, remember, is equivalent to the sum of all the elements that came before I and I itself, right? So if we already computed PSA at I minus 1, then we can get PSA at I by adding the current number to the sum of numbers that came before it. So PSA at I minus 1 is the sum of all the elements up to I minus 1, right, which you've already computed before. And in.nextInt is the integer that you're reading, and PSA at I is your current array value. So this is a sum of numbers before it. In.nextInt is itself, and PSA at I is the sum of numbers before it plus itself. And then you read the number of queries, right? So you read L and R. Why am I adding 1? It's because we shifted the PSA over by 1, remember, to avoid that negative index problem. And then we can use that formula, and everything will be all right. So let's look at visualization of this. So right now we're at 1, right? We're starting off. So PSA at 1 equals PSA at 0 plus 1. Well, 0 has nothing in it, so it's always 0, and then you add 1 to it. So this is the sum of all the elements up to 1, which is just 1. Okay, let's move on to 2. PSA at 2 equals PSA at 1 plus 2. So this array element holds the sum of everything at 1 and everything before 1. So you want to add this to 2, which will give you 3. Okay, and PSA at 3 equals PSA at 2 plus 3. PSA at 2 holds the sum of all the elements that came before it and itself, right? And then you add 3 to it, which is the number that you're reading in, and then you'll get PSA at 3. PSA at 4 equals PSA at 3 plus 4, because PSA at 3 holds the sum of all the elements that came before it and itself, and 4 is the current element. So you just add those two together to get 10, and same idea for PSA at 5. So this is why this formula holds true. So I hope that helped out a little bit. And when you're performing a query on the PSA, right? So right now, L equals 0, R equals 4, right? We want to know all the elements between 0 and 4, right? But remember, the number of trees was 5. So 4 would just be the last element, right? But we can't access 4 here because our PSA has like 0 to 5 because we shifted everything 1 over to the right. So we have to look at PSA at 5, and we subtract PSA at 0, which would give us 15. So that's why we added 1 to the left index and we added 1 to the right index, is because we shifted everything over for the prefix sum array. And then, so like L would be equal to 1 and R would be equal to 5. But then we are looking at L minus 1. So L becomes 0, right? So we take PSA at 5 minus PSA at 0 gives us 15. Yeah, so that's how it works. So let's analyze the time complexity of this code. So one thing that you might notice is now there's no more nested for loops. Therefore, it doesn't have that multiplication thing that you guys were talking about earlier. The number of loop iterations is just num queries, right? So every loop iteration, I only need to do subtraction to find the answer. I don't have to loop over everything. So you see, every single time this for loop runs, I'm only reading in 2 numbers, adding 1 to it, and then doing 1 subtraction. I'm no longer having to loop through all of the trees, right? It's not reliant on how many trees I have. It's only reliant on the number of queries I have, right? And the number of operations is around 4 times 10 to the 6, about 4 million, I think. And so that's doable for a computer. And you will pass with this code if you submitted this. But try not to copy this code when you're trying it at home. Just try to write it out from memory. Make sure you actually understand how a prefix sum array works, why it works, why do we have to shift all the elements right by 1, right? And why this formula works, PSA at R minus PSA at L minus 1. So here are some practice questions that you can do. This might seem very abstract, like how many times is someone going to tell you that I'm going to chop down all the trees from index 0 to index 4, right? So you can see that prefix sum arrays can be used in a variety of ways, right? So for example, checking a letter frequency between a piece of text, for example, I would heavily suggest practicing these problems. So let's try another problem. And you can see Rick Astley is very excited to try this problem as well. And I'm sure you are. So this problem is called battle positions. So you have 3 battle stations, station 1, station 2, and station 3. So you're kind of like an army commander. And you send 3 waves of troops that will increase the population of all stations between indices L and R by a value called K. So how many stations have less than 2 people in them after all of those waves, right? That's something that I want to know. So first, it starts off the population to all be at 0, right? And in the first wave, we see L equals 1, R equals 3, and K equals 1, which means I want to increment the population from station 1 to station 3 all by 1. So here you can see you add them all by 1. In wave 2, I'm going to increment station 2 to station 3 all by 2. And on wave 3, I want to increment just station 3 by 2. So, well, you can say, okay, I'm just going to do the nested for loop strategy here, right? I can just loop through all of this and add 1, right? Oh, second wave, well, I can loop from 2 to 3 and add 2. But wave 3, I'm just going to add 2 to station 2. So do you see kind of like the similarities between the stuff that we just did and this problem called battle position, right? In the previous problem, deforestation, you're summing up all the numbers from L to R. Here, you're increasing all of the numbers from L to R. So what's a way that we can do this? Well, that's the nested for loop solution, right? We would just read everything that we need. We have a population array. We read the left index, the right index, and the amount to increment. We will loop from L to R, and we add K to population at J. So we will add K to all of the array elements from L to R. And then we have a count variable to count how many stations have less than min troops, right? The minimum amount of troops. So I would loop through it. If the population at I is less than the minimum number of troops, then just add it to the count. And then at the end, I'm just going to print out the count. How many stations have less than min troops, right? So this is a very trivial solution, but just think about how much time that this is going to take. So why would you get TLE with this solution? Well, let's analyze the time complexity again. How many times does the code in the innermost for loop run in the worst case? I'm going to give you 2 variables. I'm going to say n equals the number of stations and q equals number of updates. So how many times would the code in the innermost for loop run in the worst case? So population at j plus equals k. How many times is it going to run? Express it in terms of n and q. Is it n plus q? Is it n times q? Is it n divided by q? Anyone have any ideas? N times q, correct. So that's, you're gonna see, well, if L equals 0 and R equals the end of the array, then I'm looping through the entire array every single time, right? So it's not very good. So yeah, we got all of that. And in this problem, it's 10 to the 5 times 10 to the 5, which is 10 to the 10, which wasn't as bad as before, but you are still not going to pass. It's too slow. So can we make it faster? Well, the answer is always yes, you can make it faster. How? By crazy math tricks, as we've shown before. So the trick here is something called a difference array. So we had a prefix sum array, and now we have something called a difference array. So the trick is to only change the endpoints of the interval L to R. So you will add k, or x in this case, to R at L, and subtract x from array at R plus 1. And after the prefix sum, the plus x will be applied to the interval L to R, right? So now we're using that prefix sum strategy again. So that's why we taught that first. So for example, I want to add 1 to the interval 1 to 4. So how would I do that? Well, in the difference array, I would put 1 at index 1. And at R plus 1, which is 5, I would put negative 1. But here you might be wondering, why am I doing this? Well, here you're only incrementing and decrementing 2 indices, which is a lot faster. So difference array is very useful when you have a ton of updates and you need to figure out something in the end, right? So here I'm only incrementing 1 and decrementing 5. And then let's do the prefix sum array thing. Let's have every index store the sum of stuff before it, right? So we have 0, and then we hit 1, so we have 1. Well, at 2, we're adding whatever that came before it. which is 1. We're adding everything that came before it, which is 1. We're adding everything that came before it and itself, which is 1. We're adding everything that came before it and itself, which is 0. So this is like some sort of magic, right? Once you apply the prefix sum array formula to the difference array, then you would just end up with adding 1 to everything. So this is when you have to do a ton of changes, and then you only have to do one prefix sum array at the end. So this is kind of the relationship between the difference array and the prefix sum array. If you have your original array, you can do prefix sums on it, and you can end up with the prefix sum array. You can do a difference on the prefix sum array, and that will return your original array. You can do the difference formula on the original array, and you'll get the difference array. You can do prefix sums on the difference array and end up with the original array. So this is a very useful diagram to take notice of. And this is the code for the difference array, right? So right now I'm reading the number of stations, the minimum amount of troops, and DA is just short for difference array, and it's num stations plus 1. And why are we shifting? Why are we adding 1 again? Well, it's because R plus 1, right? If your R is at the end of the array and you add 1 to it, well, you're going to get array index of bounds. So you need to add 1. You read the left index, you read the right index, you read the amount that you're incrementing it, and you only change the endpoints. You only want to store the differences at the endpoints, right? Because when you're updating something from L to R, nothing changes between L and R, right? So you, like in a difference array, you only have to increment the left index and you have to decrease the right index by the same amount. And then you can do prefix sums on it, right? So difference array at I, you add everything that came before it. And then if the difference array at I is less than min troops, then you can add to the count, right? Because I'm doing a prefix sum on a difference array, it's going to give me the original array. So I can do this. I can do array at I is less than min troops, then you can do count plus plus, and then you can print out the count in the end. So that's just another strategy to use. And here are some practice questions that you can do for your difference array. Yeah, so hope you guys got everything. Do you guys have any questions about how a prefix array and a difference array work? If you want to practice these kinds of problems, just look under data structures on DMOJ. Yeah, so this is making like some stuff related to array manipulation a lot quicker. So whenever you see something like between index L and R, I want you to do something to it. I want you to think about range sum, like prefix sums and difference arrays. So prefix sums is when you have to do if you have to do a lot of queries on it, right? If I'm asking you a ton of questions about what's the sum between L and R, then you would do prefix array. Difference array is I want you to update something from L to R, right? I want you to increase everything from L to R by 1. I want you to decrease everything from L to R by 1, right? It doesn't have to be 1. It could just be any kind of number, and that formula would still apply. So it's a very useful tool. Right now, we're just using it for example, updating like additions, right? I want you to add everything by 1. But in the future, when you see more complicated problems, you can actually apply this in different ways. Like if someone asks you to multiply everything from L to R, you can still use this idea of difference arrays, but you will need to do some other mathematical calculations on it. But you can still use the idea of a difference array and a prefix sum array, right? Yeah, so there's actually a ton of applications for this. Like think about if someone tells you, I want you to find out the multiplicative sum of everything from L to R. Well, you could just use the same strategy, right? Here we're doing array at like PSA at R minus PSA at L minus 1, right? This is, I want to find the sum of everything from R to L minus 1. But what if we want to find like what's everything multiplied from L to R? Well, we would just do PSA at R divided by PSA at L minus 1. So you can use this in a lot of different ways. Oop, there's an ant on my table right now. Yeah. So any kind of sum like would be used in range sum queries and difference arrays. Does anyone have any other questions? Okay. Do you guys have questions in general about CCC? Does anyone want me to show you guys how to submit problems on the CCC grader? Can I explain the difference array again? Yeah, for sure. Which slide? This slide or like this slide? Ah, okay. All right. So I'm just gonna show you how it can be done, right? So if I want to add 1 to interval 1 to 4, then I would just change these endpoints, right? If I want to make another change, like let's say it says add 1 to the index 1 to 4. And I also tell you to add 2 to the interval, let's say 2 to 3. How would I do that? Well, I would just increment this by 2. And then I would just decrease at 4 minus 2, right? And when I do prefix sum of it, then it's going to carry over, right? If I do prefix sums, then I would get 0. Well, I want to add the previous one to this, so I'll get 1. I want to add the previous one to this, so I'll get 3, right? I want to add the previous one to this, so I'll get 3. I want to add the previous one to this, which I'll get 1. And then I want to add -1 to it, so I'll get 0. So there, this would be your new prefix sum. So that's one way to do it, right? So you only have to change the endpoints of every single update. And in the end, you just do prefix sum. Every single element, add the element before it. Every single element, add the element before it. And then you'll end up with the original array. Okay, does CCC give more points to people who do questions faster? Or is time like a tiebreaker or something? I don't think, like if you're talking about honor roll, like CC honor roll, they might, I'm not sure if they do time tiebreakers or not.
I don't think, what I've been told is that there is a different cutoff every year. So last year, for example, the cutoff was 60 points, and each question was like 15 points. I think it says that on their website. Each question you do, like, each question where you get like everything correct is 15 points. So last year, if you did up to J or S4, wait, this is junior actually, junior 4, that would be exactly 60 points, and you wouldn't get honor roll. Like you wouldn't get a certificate or anything. And if you're anything above 60, then you got like special things or something. I don't know.
Yeah, so usually they wouldn't do time as a tiebreaker unless like for honor roll, unless you're like trying to make CCO, which is like the higher level contest, and they only take like 25 people or something, then they might just use time as like a tiebreaker. But for honor roll, I don't think it works like that because they have to give you like a number, right? They'll be like everyone who got above 60 would get like honor roll, right? They can't like discriminate between like what time you submitted because, well, then the cutoff number would not mean anything, right? So if there's like for example, if there's too many people who got score of 60, right, then they'll just make the cutoff 61. So
the cutoff of 60 means that people with a score of 60 are not included, by the way.
Oh, okay. Yeah. So anyways, it's like that. Usually time wouldn't be the tiebreaker.
Yep.
The year that I wrote the junior, I got 60 and the cutoff was 61. So that was kind of sad. But that was because the last problem was like insanely hard. And that's why you have to get partial points, like what Andrew did when he was solving that problem. It's better to get like 5 points from that question than to get like 0 points, right? So even when you see a really hard question, there's usually like your most simple solution would maybe pass 1 or 2 test cases. Yeah, like for example, let's see this question, right? It says for 30% of your questions, n and q are less than 1,000. Well, remember the number of operations was n times q, right? N times q is 1 million. So that's why Andrew got that 30% of the points, right? And then for 50% of the points, well, n and q are less than 10,000. So n times q, 10,000 times 10,000, you might pass some of those test cases. And then for the rest, you're probably never going to get these, right? But at least if you get 30 points from a question, like 30% of the points on a question on the CCC, that might make the difference between you not making honor roll and you making honor roll. Sometimes it's that kind of difference. So you want to get all the partial points that you can. Okay, if there's no other questions, that's the end of today's lesson. Yeah, thank you guys for coming. If you want to stay around and ask me about like specific problems that you want me to solve, I can give you some ideas. But yeah, that's the end of today's lesson.
Yep.
Hope you guys have a great weekend. Bye.
Goodbye.
You're still confused about the difference array? Okay. Okay, I'll actually do this on a Google Doc. It might be better than doing it on a slideshow. Okay, so let's say this is the index and this is the difference array. I'll call it DA. So I have index 0, I have index 1, I have index 2, and I have index 3. All right. So let's say everything starts off at 0, right? And I want you to add +2 to 1 to 3. I want you to add +3 to, I don't know, 1 to 2, right? And I want you to add 5 to 1, just 1 itself, right? Actually, I'm going to reorganize this. Okay, so if you're wondering how the difference array works, well, let's just take this. I just want to add 5 to 1 to 1, right? So this is basically means I want to add 5 to just the index 1, right? So what I would do on the difference array, well, if we're using that formula again, which is PSA, oh wait, DA at left index plus equals K, right? And DA at R plus 1 minus equals K, right? So your L is 1. So you will add 5 to here. And what's R plus 1? Well, R is also 1, but you want to add 1. So that's minus 5, right? So this is 0 and this is 0. So how does it work? Well, if I'm going to do a prefix sum array on it right now, so this would return it to the original array. Well, 0 is just 0, right? 5, I want to add everything that came before it, which is 0 plus 5 equals 5. So this doesn't change. What's negative 5 plus 5? Well, negative 5 plus 5 is just 0, right? And then 0 plus 0 is 0. So now you see that if I do this, when I do a prefix sums on it, then I'll end up with 5 at index 1. So this shows that your formula actually works, right? So when I add a 5 here, if I do a prefix sum on it, the 5 would be added all the way down here, right? I have a -5 out of it, so it negates the effect of the 5. So the reason why I do minus equals k is because I want to make sure the influence of the 5 doesn't get carried over after, like 2 and after that. I can show like a more mathematical way, I think. Like kind of when we were doing the prefix sum arrays, it was like something like this. A at 1, A at 1 plus A at 2, A at 1 plus A at 2 plus A at 3. So what I'm doing here is that like I'm trying to negate the effect of the 1 because so that like it doesn't carry over again, right? So if I do minus A plus 1 here, right, then this A plus 1 will never show up here, right? So what I'm doing here is I add here by 5 because I want everything that to come after 1 to also have that adding 5 to it. And I want everything that comes after 2 or including 2 to not include that 5 in it. So it kind of like carries over to the right. I know like my explanation probably isn't too good, but well, just to like think about it, like how does this difference array work, right? What does this work when I do +5 and -5 here? And when I do the prefix arrays here, I just end up with a 5 here, right? And then if I want to add 2, for example, to 1 to 3, well, I just need to add 2 to 1 to 3. Well, I'm just going to add 2 here. And I'm going to -2 here. And I want to add 3 to 1 to 2. Well, I'm going to add 3 here. And 3, I'm going to -3. So at the end, I'm going to end up with 10 here, -5, -3, and -2. And then when I do prefix sums on it, so this would be 10, this plus the one before 5, this plus the one before, this plus the one before is 2, right? And this plus the one before is 0. So if you're doing the difference array, you're always going to end up with 0 at the end, no matter what. If you're not ending up with 0, then you've done it wrong because index, it's not supposed to work, right? Like index 4 does not really exist in the original array. So it should end up at 0 in the end. Yeah, I'll come up with a better explanation and I'll let you guys know. I'll probably put it in the Discord. So does it only work with the arrays that start with only zeros? No, it can work with one indexed arrays as well. You would just, yeah, it would work either way. Like you would just never touch index 0. If it starts at index 1, you can always leave index 0 the way it is. Like you would just not touch this index at all. And then you would just do, because L would at least would just be 1, right? So this would not affect anything. Because 0 added to 1 is always 1, right? So you would just never touch this index. Oh, wait, does it only work with the array? Oh, okay, I misread your question. So the way you would do that is you would keep the original array, right? So let's say my original array was like 0, 1, 2, 3, 4, and maybe you have some random numbers to it, like 5, 3, 2, 1, 0. Something like this, right? And I'm doing all of these additions and subtractions to it, right? So I end up with 0, 10, -5, -3, and -2. Well, I would just do prefix sums over this, right? I'm doing this on the difference array. I'm not doing it on the original array, right? I'm doing this on the difference array. So This should not be here. So let's do prefix sums on the difference array right now. So 0 plus 10 is 10. 10 plus -5 is 5. 5 plus -3 is 2. 2 plus -2 is 0. So now you have, this is the new original array, right? Well, then I would just add everything back to your starting array. What's 0 plus 0? 0. What's 10 plus 5? It's 15. What's 5 plus 3? It's 8. And what's 2 plus 2 is 4. So I would just do the difference array, do the prefix sum array on the difference array, and then add everything in this array back to the original array. And then you'll get your new updated array. Yeah, so step 1 is make difference array. And then second step is do prefix sums on the difference array. And then add everything in the new array back into the original array. And then you have, you have your new update array. So originally we were like assuming that everything's going to be 0, right? But now that you have your new original array, you would just add everything in the new original array back into the old original array, and you'll get the same answer. Okay, do you guys have any more questions? Prefix sums is just PSA at I equals PSA at I minus 1. Or you can call this ARR. And here you just do ARR at L plus plus, and then ARR at right plus 1 minus minus. And here you're just doing original at I plus equals the new one at I. Yeah. This part might be hard to understand why this step 2 works, but hopefully you understand how the step 3 works. Yeah. Okay, any more questions? Oh, the original array thing is just like what the array is supposed to be if you just did it the naive format, right? Like if I just added these to the original array like that, then I'll end up with this. Yeah. Then you just need to add it back into the array that you already had before.